Okay, now let's talk about some specific examples of FIR filters and how they're used in practice. Our first example is we've got a signal that's got some 50 Hertz noise coupled into it. So the top left signal is our signal, which is a 500 Hertz sine wave. And our top right signal is our signal, which is our noise signal, some 50 Hertz noise. And you notice the magnitude of that noise is a bit shorter, a bit smaller than the magnitude of our signal. Now we could adjust the magnitude of either of those. Now if we add them together, you'll see that we have our 500 Hertz signal, but we also have that 500 Hertz signal that's, the signal's going up and down, but it's actually being offset by the noise. And so we have that convolution of those two signals together, which causes some unusual behavior there. Now, if we use a Fourier transform on that signal, we see what's just above us, where we see two peaks. One peak at 50 Hertz, which is the lower peak because the magnitude of that signal that's contributing to the noise is lower. And then we see our higher peak, which is our 500 Hertz peak. So how do we design a filter in Matlab to get rid of that noise and give us just the signal that we're after, the 500 Hertz part? Well, what we can use is if you go to Matlab and you type in the command design filter, this brings up the menu at the top there, which says, well, essentially what type of filter do you want? Do you want a band pass or a band reject, a low pass or a high pass? And so in this case, we'll select a band reject filter because we want to filter out that 50 Hertz part and keep all the other stuff as it was. And then it'll bring up another menu that will basically ask us a number of questions like, what are our cutoff frequencies for the low side and the high side? What's our sampling frequency? All of these sort of things. At the end of that, it'll basically dump us out a filter. It'll say, okay, if we want to use this filter, it's called design filter, band stop FIR filter. And then it copies in all of the different values that we need to run that filter. Now, we need some code around this to make it do everything else. So I've got some demos of the code here that I've actually used to generate all these graphs. So the first part of it is really just generating that signal, the 500 Hertz signal and the 50 Hertz noise signal, copying them together, which is just adding one signal to the other signal. Then plotting them so we can actually see those different signals. Then I've got the filter that's been created there, and we apply the filter to that actual data. Then there's some more code that will basically apply the Fourier transform to that original noisy signal and to our new signal. And we can graph each of those and look at the difference in the Fourier transform, the spectral analysis of this. So before we get into that, let's look at the filter response. Matlab will show us what the filter response looks like. And here's essentially our filter. We see that outside of that band from about 40 to 60 Hertz or so, we've got a tiny little bit of ripple, but essentially no attenuation on our main signal. And then during that area, we have this sharp drop off where any signals around that area will be filtered out. Okay, let's look at the results of the filter. We see the same graphs that we had there, those first four, and then we see our new graphs. The filtered signal here looks almost exactly the same as the original 500 Hertz signal. And then we see the spectral analysis of this filtered signal, and we see that we've taken out almost completely that 50 Hertz noise that we had in there, and we've just got that single peak there at 500 Hertz. So we can be sure that we've removed our noise here, and we've just got our single frequency here, which removes everything else. So that one was an example of a band stop filter. Let's look at a low pass filter. Once again, two signals, one at 220 Hertz and one at 500 Hertz. If we add those together, we see this weird collection of bumps and troughs and hills. And we see once again, if we look at the spectral analysis of it, once we run a Fourier transform on it, we've got two peaks, one at 220 Hertz and one at 500 Hertz. Now, we might want to have lower frequencies here and cut off everything above a certain frequency. So here's the code I've used to generate this. So first bit is basically generating those two signals, plotting those two signals. we've got our filter there, and I did a very similar thing. I used the design filter function, and that generated that block of code for me, which is my actual filter. Here we've specified a pass band frequency of 300 Hertz and a stop band frequency of 350 Hertz. So at 300 Hertz, we'll start attenuating, and by 350 Hertz, that will be the bottom level of our attenuation where we're bottoming out. We then apply that tool to the data, and then we need to do our Fourier transforms as well and show what our frequency spectrums will look like before we remove the noise and then after we remove the noise too. Okay, before we look at those frequency spectrums, let's look at our filter performance. Here's our filter performance. Essentially, we see up to around 300 Hertz, we've got almost a flat signal, a tiny bit of ripple in there. We hit about 300 Hertz and the filter drops off sharply and then goes quite low. And we've got heavy attenuation, anything over 350 Hertz. So let's look what it looks like in practice. We see down the bottom, these two graphs here, the final result, the filtered result, looks almost exactly the same as the original 220 Hertz result before we added the noise into it. And we see at the different spectrums here, we've completely removed that 500 Hertz noise that we had there, and we've just got the 220 Hertz frequency spectrum density that we have. In terms of practically applying these sort of filters to our data, a few things to think about. One is, well, maybe we can remove some of the noise before we actually get this into the digital domain. There might be some things that we're doing that are actually creating noise in our system. Maybe our wires are too long, our cables are too long, or not shielded properly, and we're picking up extra noise. We might be able to reduce that before it gets to our system. So we might be able to do less digital filtering or remove the need for it altogether. But assuming we've done that already and we're still getting some noise in the system or undesired frequencies that we want to filter out, well, we need to think about what filter type that we're going to use. Is it going to be a low pass filter, a high pass filter, band reject, or band pass filter? One recent example I was dealing with, one of my students was using a little LiDAR, and the LiDAR was producing range data really well, except occasionally, every couple of seconds, it would produce a massive spike. It might be measuring 150 centimeters and then would jump up to 40 meters momentarily just for one signal sample. With this fast moving data, you'd be looking at using a low pass filter. So we've got our low frequency, our data changing at a low frequency, but whenever we have something high, well, if we use a low pass filter, it will take out some of those high values. That's something that we'd want to do. We'll want to select our cutoff frequency. So how quickly can our data change? And based on that, we'll probably, the best way to do this is probably to load it into a Fourier transform, look at the frequency spectrum of our data and say, oh, we want to remove those ones, and that should clean up our data nicely for us. And then we can use Matlab to create our different filter. We specify what type of filter, what our cutoff frequencies are, and Matlab will tune an FIR filter to those particular frequencies that we're after.